Imagine a world where computers can learn from experience, just like humans. This is the promise of artificial intelligence. AI algorithms are the building blocks of this technology. They enable machines to analyze data, make predictions, and even perform actions. AI algorithms are revolutionizing countless industries. They power everything from self-driving cars to personalized medicine. Understanding these algorithms is key to unlocking the full potential of AI. In the vast universe of AI, there are many types of algorithms. Each type has its own strengths and weaknesses. Let's embark on a journey to explore the fascinating world of AI algorithms. Supervised learning is like learning with a teacher. Imagine a classroom where a teacher provides students with labeled data. This data consists of inputs and their corresponding correct outputs. In supervised learning, the algorithm learns from this labeled data to make predictions on new, unseen data. It's like training a dog with treats. The algorithm learns to associate specific inputs with desired outputs. Supervised learning algorithms are used in a wide range of applications including image recognition, spam detection, and medical diagnosis. They are powerful tools for tasks where we have labeled data and want to predict outcomes for new data. Unsupervised learning is like exploring a new city without a map. Imagine being given a dataset without any labels or instructions. It's up to you to find patterns and relationships within the data. In unsupervised learning, the algorithm is tasked with finding structure in unlabeled data. It's like discovering hidden constellations in the night sky. The algorithm identifies clusters, patterns, and anomalies without explicit guidance. Unsupervised learning algorithms are used for tasks such as customer segmentation, anomaly detection, and dimensionality reduction. They excel in situations where we need to uncover hidden patterns or group similar data points together. Reinforcement learning is like learning to ride a bike through trial and error. Imagine an agent interacting with an environment. The agent takes actions, receives feedback in the form of rewards or penalties, and learns to maximize its rewards over time. In reinforcement learning, the algorithm learns by interacting with its environment. It's like playing a video game. The algorithm learns to navigate the game world and achieve its goals through trial and error. Reinforcement learning algorithms are used in robotics, game playing, and control systems. They are particularly well suited for tasks where an agent needs to learn optimal strategies through interaction with its environment. Section 5. Linear regression. Predicting the future with data. Linear regression is a fundamental algorithm in supervised learning. It is used to predict a continuous target variable based on one or more input variables. Imagine trying to predict a house's price based on its size and location. Linear regression assumes a linear relationship between the input and output variables. It finds the best fitting line that minimizes the difference between the predicted and actual values. This algorithm is widely used in finance, economics, and healthcare. For example, it can predict stock prices, forecast economic growth, or estimate the risk of developing a disease. Section 6. Decision trees, making choices with data. Decision trees are another powerful tool in supervised learning. They are widely used due to their simplicity and effectiveness in making decisions based on data. They are used for both classification and regression tasks. This versatility makes them a go-to method for many data scientists and analysts. Imagine a tree-like structure where each node represents a decision based on a specific feature. Each branch represents the outcome of that decision, leading to further nodes and branches. Decision trees work by recursively splitting the data into subsets based on the most significant features. This process is known as recursive partitioning. The process continues until a stopping criterion is met, resulting in a tree that maps input features to predicted outputs. This stopping criterion could be a maximum tree depth or a minimum number of samples per leaf. These algorithms are used in various fields, including customer relationship management, fraud detection, and medical diagnosis. Their ability to handle complex data sets makes them invaluable in these areas. They are easy to interpret and can handle both categorical and numerical data. This interpretability is crucial for stakeholders who need to understand the decision-making process. Moreover, decision trees can be visualized, making it easier to explain the model to non-technical team members. This transparency is one of the reasons why decision trees are so popular. In summary, decision trees are a fundamental tool in the data scientist's toolkit. They offer a balance of simplicity, interpretability, and power, making them suitable for a wide range of applications. Section 7, K-means clustering, grouping data into meaningful clusters. K-means clustering is a popular algorithm in unsupervised learning. It is a cornerstone technique in the field of data science and machine learning, often used to make sense of large datasets without predefined labels. By identifying natural groupings within the data, K-means clustering helps in simplifying complex datasets into more understandable clusters. It is used to partition data into K-clusters based on their similarity. The value of K is predefined, and the algorithm works to find the best way to group the data into these K-clusters. This process involves calculating the distance between data points and assigning them to the nearest cluster. Imagine grouping stars into constellations based on their proximity in the night sky. Just as stars that are close together form a constellation, data points that are similar to each other are grouped into clusters. This analogy helps in visualizing how K-means clustering works in a more intuitive way. K-means clustering works by iteratively assigning data points to the nearest cluster center and updating the cluster centers based on the mean of the assigned points. This iterative process continues until the cluster centers no longer change significantly, indicating that the algorithm has converged to a solution. The algorithm aims to minimize the distance between data points within the same cluster. By doing so, it ensures that the data points in each cluster are as similar as possible to each other, while being as different as possible from data points in other clusters. This algorithm is widely used in market segmentation, image compression, and document analysis. In market segmentation, it helps businesses identify distinct customer groups, allowing for targeted marketing strategies. In image compression, it reduces the amount of data needed to represent an image by grouping similar pixels together. In document analysis, it helps in organizing large collections of documents by grouping similar ones together. It helps uncover hidden patterns and group similar data points together, providing valuable insights from unlabeled data. By revealing these patterns, K-means clustering enables data scientists and analysts to make more informed decisions, ultimately driving better outcomes in various applications. Section 8. Q-learning training machines through trial and error. Q-learning is a model-free reinforcement learning algorithm. This means it doesn't require a model of the environment to learn how to act optimally. Instead, it learns from the consequences of its actions, making it highly adaptable to various scenarios. It is used to find the optimal action selection policy for an agent interacting with an environment. The agent explores the environment, taking actions and receiving feedback in the form of rewards or penalties. Imagine training a robot to navigate a maze without any prior knowledge of the maze's layout. The robot starts with no information and must learn the best path through trial and error, gradually improving its performance. Q-learning works by learning a Q function that estimates the expected reward for taking a particular action in a given state. This Q function is updated iteratively as the agent gains more experience. The agent uses this Q function to select actions that maximize its cumulative reward over time. By continually updating its Q values, the agent becomes better at predicting which actions will yield the highest rewards. This algorithm has applications in robotics, game playing, and control systems. For instance, in robotics, Q-learning can help robots learn to perform tasks like picking and placing objects or navigating through complex environments. It enables agents to learn optimal strategies through trial and error, making it suitable for complex and dynamic environments. This adaptability is crucial for real-world applications where conditions can change unpredictably, requiring the agent to continuously learn and adapt. Section 9. The Future of AI, From Algorithms to Real-World Applications. We have explored the fundamental types of AI algorithms: supervised, unsupervised, and reinforcement learning. We have also delved into specific examples of algorithms within each category, understanding their applications and how they learn from data. The journey of AI doesn't stop here. These algorithms are merely the building blocks of a much larger and more intricate world. In our next adventure, we will explore the real-world applications of AI, from self-driving cars to personalized medicine, witnessing how these algorithms are transforming our lives.